This is an inverter board from a Samsung induction range cooktop, and I wanted to take the filter, the line filter, and just separate it out of it. So this is the second half of the board. The other half I took all the components off from the filter. So it constitutes 1, 2, 3, 4, 5, 6 components, plus these two over here that actually shunt to ground. So all these components I put in series, and I'm going to show you that circuit right now. Alright, so here's the circuit. On this side I have the input, and this is actually how it's lined up on the board, pretty much in a series fashion. It's kind of hard to tell from the board just because the way they constructed it, but here you have some filter caps, and they're meant to filter out low and high frequencies, and they actually act along with the rest of the circuit to do that. The large inductor you see here, also sometimes called a choke. The choke will resist changes of current flow. So if you have a sudden dropout of voltage, it's actually going to act as a capacitor for current. So the capacitors store voltage, inductors store current, and the magnet inside will increase exponentially the amount of inductance of the wire that's wrapped around. So these two right here, these two capacitors, they go to ground, and that's why I left this wire hanging, because there's no need for it. It's not an active part of the circuit, these two right here. And we have one last filter cap, and then this goes to the DC rectifier, the bridge rectifier. So Kurt, in one of your circuits, I think before you had one of these caps that was blown, okay? And so if it short, the cap, they have their films that are wrapped many times around, and so what can happen is if that internally shorts, then it'll cause very, very high current and then just kind of explode. So what will happen then is you just have an open circuit in place of one of these caps. The actual AC mains are still fine, but it won't filter properly any interferences that come through the input mains. Alright, so this is what happens when you put the 60 Hertz sine wave, 20 volts peak to peak, on the scope. You can see it's 20.6 volts here, 60 Hertz, and I put these cursors up here so that we could have a reference when we change the frequency. So I'm going to go ahead and set it on 1 kilohertz and see how it does. Okay, so that's 1 kilohertz at 20 volts, and you can see it's actually half, so that's about 10 volts peak to peak. Okay, and there I switched it to 100 kilohertz. 20 volts, 100 kilohertz. It's basically completely filtering out that signal. The scope at this resolution is not even registering that there's any frequency there at all. Now, if we get rid of the cursors and zoom in on the resolution, there's our signal. So basically what we're looking at is 20 volts per division, or sorry, 20 millivolts per division, 1, 2, 3, 4, 5. So basically 100 millivolts, a little more, between 100 and 120 millivolts. And that's how much this is filtering out. So it starts off at 20 volts, filters it down to 120 millivolts. Okay, now this is the same filter with 1 Hertz at 20 volts, and you can see it is filtering the other way as well. So the higher frequency it goes, the more it filters out that frequency, but also the lower the frequency it goes, the more it filters out the frequencies. So they designed this circuit so at 60 Hertz, Basically, it would be a resonance frequency acting as a clear and open path for the 60 Hertz signal of any amplitude.